Daniel Sigg is a senior scientist with Caltech working at LIGO Hanford Observatory in Washington. He is responsible for coordinating the commissioning effort at Hanford and for bringing the advanced LIGO detector to full sensitivity. He got his PhD degree at ETH Zurich and joined the LIGO project in 1995 with MIT. His current research interests include gravitational wave astrophysics, precision measurements, and large-scale optical interferometers. Please join me in welcoming him.
And this, of course, everybody knows this all started with Einstein's theory of gravity in 1915. What's a little less known, but also immediately afterwards he made a weak field approximation where he actually derived gravitational waves, so they became basically part of the theory from the very beginning. But back then it's already recognized as going to be a very weak phenomenon. What are gravitational waves? I'm showing they're propagating in this direction. They're transverse waves in sort of a quadrupolar thing. You can think of them as a wave that stretches in one direction and shrinks in the other direction, and sort of every quarter wavelength that changes. On the right side here, I'm writing the effect. The effect is sort of linearized as function of the metric, that the Minkowski, and this is the additional stuff where the gravitational waves will be. And this is sort of the formula of a source. And this I is a changing quadrupolar thing. It's a little bit like electromagnetics. You find one-to-one equivalences between those two. And the effect here on the side, if you put in some numbers, if you put in the mass of a black hole, solar mass, put it about a billion light years away, the effect you have to think about here measuring about the size of a proton radius. So even though you start off with a lot of energy, at the end of the day, space is very stiff, and you have to make a measurement that is extremely small. Do we know gravitational wave exists? Yes, we do. We actually know that since quite a while. There's the famous double pulsar that Hall and Taylor discovered. And what they're seeing is these two pulsars going around each other, and you have a very good clock by just looking at the clicks of these neutron stars. And you can actually see that the orbit decays. The orbit decays because it emits gravitational waves, so it loses energy, it comes closer and closer together. This is too weak a source for us. First of all, it's very slow. It's like an 8-hour period. And the other thing, it still takes about 300 million years before that actually coalesces. What we are actually looking for is sort of the endpoint is the entire process. So we know these sources exist. We know they emit gravitational waves. And that agreed very well with theory. Moving on, if you look at gravitational wave spectrum, you can start all the way down at the Big Bang up to maybe the highest frequency process we can think about is something like a supernova, when you have an explosion on a very small scale. There are multiple experiments out there that are trying to address the entire frequency space. There is the CMB polarization background with the biceps, where they look at tensor polarization things in the background. There is pulsar timing thing. You can just use pulsars you see as clocks, and there is a gravitational wave, very long wavelengths. In this particular case, traveling between us, it changes the arrival time of these pulsar timing signals. And if you have enough pulsars, you can sort of invert backwards what kind of gravitational waves, more sort of in a stochastic way, go through the universe. And you can look at things like the merger of two galaxies, where the two black holes at the center of these galaxies are merging. There's a space-based interferometer project, the LISA project, that looks at compact binary inspirals on the extreme mesh ratio inspirals, things like one stellar mass black hole spirals into a central mass hole of a galaxy. That will be a good source for a space-based interferometer. And for terrestrial interferometer, with the rest of my talk, we'll almost exclusively talk about it. We can think things like pulsars, supernova, and also, of course, compact binary inspirals. What are the sources we have here? The one we actually discovered are coalescing binary systems, either black holes or neutron stars. There are, of course, other things you can think about it. The supernova I already mentioned. A neutron star, if it's not completely symmetric, and of course it rotates, it can actually emit a very weak signal. It's extremely weak, but it's there for a long time, so it can integrate over a year or multiple years to try to find it. And of course, you can also do, if you have more than one detector, you can cross-correlate them and start thinking or looking about the cosmic microwave background. And this is certainly a long shot in our current detectors because the sensitivity is nowhere near where it probably need to be. And of course, there's always a potential to see something completely unexpected. So terrestrial detectors started very early on with Joseph Weber, and he built us a bar detector. It's a big piece of aluminum. If you actually ever visit LIGO Hanford Observatory, that bar is right there in the entrance hall, so you can actually look at it. One of the maybe unfortunate thing, he immediately saw gravitational waves. This later on turned out to be not true. But it certainly created a lot of momentum in the field because other people started building similar bars trying to see the same things. Later on, it was realized that the Milky Way should actually be losing energy at a noticeable rate if this would have been true. So this wasn't really a good way to do it, mainly because you probably will never be sensitive enough to actually do it. So not this way. We're of course coming to finally the interferometer, a Michelson interferometer. And why is that a good idea? Because I'm talking about this quadrupolar wave. So if you think of it, they're coming through the plane, they're doing a stretching one direction, making the other one longer. And that's exactly what a Michelson interferometer is good measuring. The difference between arm lengths, or in this case, timing difference between the two photons, beams that are going down each arm. On the right, I have the antenna pattern for the two polarization. So compared to electromagnetic antennas, we are not very, or telescope, we are not very sensitive to a direction. You're basically seeing everything that's up here and it's down there, not a little less in the plane. So a single Michelson interferometer can detect something, but it can't really tell you where it comes from. This field really started in '71 with Ray Weiss, and his contribution was actually showing how you can actually do a program and actually achieve that on Earth. And that's the first time when we realized that we actually have to build it long. You can't build it in a lab. You have to go to kilometer-long laser interferometers. The main reason is actually a thermal noise to make that happen. So these are the current situation of gravitational waves observatories on Earth. There are a total of 4 currently operating. The GEO project is a much smaller project that doesn't really have the sensitivity of the 2 observers that detected the first gravitational in-spiral at LIGO Hanford and LIGO Livingston Observatory. Currently, we also have the Virgo Observatory in Italy. That's very good. Now we have 3 observatories. We can actually do triangulation. There are other projects. The next one that's probably going to come online is the Cagra project. That's a 3-kilometer underground project. Hopefully in the next 5-10 years, they're going to be online, and then they can do other things. And finally, we have also a LIGO India project. The LIGO project built 3 interferometers. We decided it's more useful to install them somewhere else on Earth than actually install them in the same vacuum envelope. So that's where the LIGO India project came about. They're still in a planning stadium. The idea is the Indian government provides the whole facilities, and we're providing the detector. So we can have a worldwide network to detect these sources. So here is a picture of the LIGO Livingston Observatory. This is 3 miles or 4 kilometers long, and the same in this direction. This is the central corner station. You see there are the cars here as to scale. Here's the Virgo detector. They all look very similar. The main difference tends to just be what's around here. This is the LIGO Hanford Observatory with some sort of nuclear stuff there in the background. Here is the actual Michelson interval we're actually using. You see it's a little more complicated. You still see the beam splitter here, you see a laser here, and you see end mirrors or end test masses here. But to actually make the thing more sensitive, we do a thing here adding an optical resonator in each arm cavity that enhances the light stored in the arm cavity by about a factor of 100. We're doing something else. If you do that and you have very low losses, the light comes in, comes back in. If you're operating this Michelson interferometer near a dark fringe, most of the light that doesn't get absorbed, and for a single pounds here, that's about 98%, would all go back to the laser and waste it. We don't want that. So we make another optical cavity, and if you do it right with the partial transmission mirrors, you're going to match it so that effectively there's no power going back to the laser, and the entire power is burned or sort of lost inside through absorption inside or scattered inside the interferometer. And that's sort of the maximum you can do with a given laser. So in this was the first LIGO observation run. The laser was about 25 watt, we had about 100 kilowatt laser beam in each arm cavity. We have another mirror here. It's called a signal recycling mirror. It has to do with the shape of the signal. But one important point here is that all these cavities have to be kept on resonances. So you have 4 coupled cavities and this dark port condition. That's a highly coupled nonlinear system that all have to be kept on operating locked using servo control systems. Here's a little bit of timeline of this project. So we're at this for more than 20 years, so it took quite a long time to actually get there. Here are a couple more pictures. The test masses, you can't bolt them down on the Earth because the Earth moves about a micrometers just from, because it's so deep down, it's actually liquid. So what we have to do is isolate the test masses from the ground so they become free masses. We're doing that with a pendulum. Pendulum is a very good way to isolate stuff. If you move the suspension point above the eigenresonance of this pendulum, the bottom doesn't really move that much. So if one pendulum is good, and clearly 4 pendulums are even better, that's why you have a quadruple pendulum system here. You see some vertical blade springs on top, but there are basically 4 stages here. These test masses are about 40 centimeters in diameter. This structure around it is not to actually hold the whole thing up, but that's mainly sort of to prevent if something breaks, the thing doesn't fall to the ground. So there is no connection from this aluminum structure to the actual test masses. Here is sort of the inner part and sort of free hanging. That's actually important, it's really free. If it starts rubbing, the whole thing is not going to work. The entire thing, the lower stages here, is a monolithic silicon construction where the thing is basically glued together. The actual test masses, that's actually quite an achievement to get the surface quality we need to make these test masses. I'm not going through the thing, but that is a non-trivial process to actually get the metrology, the manufacturing, and make those good enough for us. The vacuum system, you can't really operate these lasers beam in air because there's Rayleigh scattering and it would not work at all, so you need a big vacuum system. This is about eye height here. So these are a very large system here where this is the beam splitter. This is one of the input test masses, and then 4 kilometers down this, you get the end test masses with the laser back here where you can't see it. This is a seismic isolation system. This quadruple pendulum is not enough to actually give enough isolation to isolate us from the ground. Gives us about 5 to 6 orders of magnitude isolation at 100 hertz. We need another 4 to 6 orders of magnitude isolation. This is actually an active system. It's a little hard to explain, sort of because of constraint in space. These are sort of a double platform system that's sort of inside-outside construction. But you can trust me that the inner stage here is not actually connected to the outer stage. There are independent stages. There are actuators on this system, and there are sensors on this system. So we can actively, on each platform, measure how much motion we have, and with servo system take that out. That's mainly the biggest motion on Earth is driven by ocean waves hitting the shore, and then we get the microseismic activity, which leads to a micron or several microns of RMS motion around 0.1, 0.2 hertz. And that's a very large motion. That's more than the wavelengths of our lathe. So we need to get rid of that motion, otherwise this wouldn't work. So there's an active system that gets rid of most of that motion, and then there's a more passive system with this quadruple pendulum that gives us the additional isolation to get really this very small displacement sensitivity we need. This is sort of an input chamber. You see people working on it. The other thing that's the enemy of all high power laser beams is dust. So we have to be very careful to keep the dust down, because otherwise you have this contamination, and then you get heating effects, or in worst cases you can shoot. You have enough heating that you shoot a hole in the mirror. This is the actual laser system. It's very clean. Again, here that's even worse. This is actually in air, so this is actually operating in a clean room. The beams are a lot smaller, so laser density are quite high. Here's the control room. It looks like any other control room, bunch of computers and monitors. And so here is sort of an outline of our observational runs. The first one, where we discovered a double black hole system, happened in 15-16, and the second one just finished last year. And in this case, we also had Virgo joining us for this double neutron star discovery, where we actually had 3 nephrons running. We are thinking of the third run will probably be in the end of this year, beginning of next year's, hopefully with almost improved sensitivity. The final sensitivity is about 180 megaparsecs in the current generation of instruments. Here you see quickly how much improvement we made in sensitivity. This is sort of the green stuff with initial LIGO. This is where we currently are. See, there was quite an improvement between initial LIGO and the current sensor. It sort of explains why we actually saw something in advanced LIGO and we didn't see something in initial LIGO. The real sources are sort of just hidden between those two lines, so to speak. And so moving on to the actual two discovery. The first one, a double black hole, and here a double neutron star merger. This is a signal we saw first on, and you can this is the signal out of the detector. It's not exactly the raw signal because we applied a bandpass filter. So all the frequencies sort of below 20 hertz were filtered off, and all the frequency above a couple 200-300 hertz were filtered off. But apart from that, this is the signal as measured by the detector. So you can very clearly see there is a signal here. This is the raw signal out of the detector. The red one here is sort of shifted, the Hanford thing shifted into the Livingston thing, and you can see you measure the same signal in coincidence. There's some general relativity simulations, numerical relativity. You match up with the thing. This is a time frequency plot, and we can very clearly see that there is a sort of a chirp signal in both of those detectors. The amplitude, the peak amplitude here is about a 200th of a proton radius. In the meantime, we have a couple more detections. So this is the zoo of black holes we discovered so far. And maybe the one thing you see here, they're actually quite large. This, of course, gave it a Nobel Prize last year. And a couple of things you can do. This is sort of a post-Newtonian approximation. If you do that in general relativity, you can sort of parameterize general relativity, and then you can ask your question, is the thing we measured compatible with what you're expecting from general relativity? And that is sort of put in sort of a dimensionless factor here, where 1 means if there is an expectation by general relativity that this thing is basically 1 plus minus 1. And the best limit here come from this double pulsar system, but of course they're mostly sensitive to the lowest order stuff because they're far away. Once you're a black hole that's merging, these higher order corrections are no longer small. So we actually start being sensitive to stuff up here. Again, because this is a single the noise of 25 event, theirs are still of order 1, but they're no longer of order 1,000 like previously. The other thing you can do, you can make a limit on the graviton mass, because this is a chirp. If the graviton has a mass, there is a dispersion, so this chirp signal would actually sort of start slowly dispersing away from each other, so we can test for that. And the limit is about 10 to the 13 kilometers. That is not much better than, that's very comparative with the solar system limits, but it's not not much better. There are also some astrophysical implications. First of all, these black holes are too big to be actually produced in our own galaxy. That has to do with the fact that once you have metals, and in astronomy everything beyond helium is a metal, so if you have heavier elements, you can't really make that big a star anymore because it sort of condensates. On the other hand, early in the universe, when there was only hydrogen and helium up, you can make enormously large stars, 100, 200 solar mass stars. So what we think, these things are still stellar black holes produced in an early universe or in a place of the universe where the metallicity is still very low. We can actually determine it has to be at least a quarter of or less of the galaxy's value. The other thing you can think about is how these things are actually forming. There are two scenarios that are still sort of people think are good candidates. One is sort of you have a double star system. One star goes supernova, produces a black hole. The other star goes supernova, black holes, and you end up with a double black hole system. There's a little magic that has happened here in between, where there's a common envelope development where the things have to merge a little bit. Otherwise, if they're just too far away, they're never going to merge in the Hubble time. That's obviously not good. The other scenario here is in global clusters. You can just make individual black holes, and then in three-body processes, you make binaries, and they're eventually merging. We can't distinguish between these scenarios with the sources we do have. You can think of it. In this case, the spins are probably more likely aligned, where here the spins are completely random. So if you have enough sources, you can probably distinguish those two scenarios. I'm gonna skip this one here. Maybe just saying here, this was the first 3 detector discovery, and you can sort of see how much difference it makes. If you just have the 2 LIGO detectors, you get these huge bananas, which is sort of useless for an astronomer to find anything. Once you have 3 detectors, you get actually a relatively small area in the sky. And as it turned out, with the double neutron star discovery, it was actually very useful to actually find the source. So once you have black holes are dark, so you don't really expect to see anything in with telescope. Of course, in a binary neutron star, the exact opposite is true. You expect to have a lot of light. You expect gamma ray bursts, depending on what's happening in this particular case. The thing is a kilonova, you see infrared light, you see radio waves. In this particular case, we didn't see any neutrinos, mainly because the thing is too far away. So here is the actual neutron star merger signal. Again, the signal is pretty clear if you look in time frequency plot. If you actually carefully look here, you didn't actually see it in the vertical thing. That's not because they're not sensitive enough, but there are zeros in the antenna pattern. That's still those zeros are pretty well defined, so it's still useful for directional things. So this still contributed a lot in pointing, even though we didn't see it. It's just an accident where it comes from. The other thing we see sort of the overlay on top of here is sort of the short gamma ray burst, and you can see that the gravitational waves came 1.7 seconds before that. So obviously you can just immediately design the speed of gravity and the speed of light are the same in 1 part to 10 to the 15, since this was like 100 million light years away. You can actually also make a constraint on the weak equivalence principle, because strictly speaking, of course, these two things also have to travel along the exact same path. The Shapiro delay is estimated to be about 1 year in this signal. So the weak equivalence principle has sort of been verified in 1 to 10 to the 7. This is sort of how the different signals, how the thing was identified early on. There is some gamma ray thing, there's still very large things. The light green stuff, and there's also a thing down here, is sort of what LIGO could do. Then if you added Virgo in here, you had a relatively small, I mean, for astronomers, still a very large area, but they were actually able to find the counterpart. Here is sort of different UV, X-ray, gravitational waves, and this is sort of announcement when stuff was announced. And you can see that basically it seems to be like at some point almost every telescope on Earth was pointing in that direction. And you can also see here when it was first measured, so obviously the first thing that actually happened with the gravitational waves, it came like a 1.5 seconds later, there was an X-ray burst, the gamma ray burst, and then the whole thing developed this kilonova. There's a relatively long time you had to wait here that just had to do with where the observatories were positioned on Earth. Sort of just missed South Africa. You had to wait till the telescope in South America were up and running. So this is sort of a plot you can find on a website. The whole thing is a kilonova, and there are tons of astrophysical papers out there describing this event, and I think they're still looking in the radio for that. Probably most people in this room were grown up with the saying that hydrogen and helium were produced in the Big Bang. All the other elements were produced in supernova explosions. That turned out to be not totally true, because all these elements here, that bright yellow, are actually very difficult to produce in supernova, because you need an R process. That's fast capturing of neutron. So where do you have a lot of neutrons? In a double neutron star coalescence. So it's now thought that all these yellow things, and things like gold and silver, were actually not produced, mostly not produced in supernova, but mostly produced in double neutron star mergers. And the amount, I think I once heard, I think there are several Earth masses of gold produced in this explosion. So that's quite a stash. What was alluded to yesterday, what you can do, the one thing is when from the chirp you can get to the masses. That just has to do how fast it goes and how fast it chirps up. So that makes them a standard candle, because if you know how massive it is, you can actually calculate exactly how much gravitational wave they emit. So binary in-spirals are perfect. You don't need a distance ladder. You can directly, from the waveform, get the luminosity distance. For black holes, the problem, of course, you can't really do cosmology, because you don't really know how far away they are, because you don't know the host galaxy. You don't have a redshift. In this particular case, for the neutron star, we do have. Here we show the Hubble constant, and we get the Planck value, and we get the values from the supernova. There's this contention a little bit, I think 2 or 3 sigma. What we can do is sort of this blue thing, So the good news is, yes, we can do it. The bad news is we're probably not that competitive. And it probably takes a while before we reach a precision that has already been achieved by the other experiments. But if this contention stays, or actually gets more significant, this will be a very good third independent test of what's really going on here. So now I'm switching a little bit gears. So this is mainly thinking about, what are we going to do in the future? Once we have something, of course, you want to really move on. So there is a short-term upgrade. Short-term, these things means the next couple of years, 5 years. Obviously, we need to first finish advanced LIGO and make a lot of measurement, year-long measurement. After that, the first upgrade is thought to be A+. You basically take the current detector, make it a little bit better. Target is sort of a 1.7 increase in the range. Further down the road here, maybe 10 to 20 years, something called LIGO Voyager. You can actually replace these test masses with silicon, go at different wavelengths, and probably get another, and start cooling that to 123 kelvins. You can get another factor 2 or so sensitivity. Much further down the road, we sort of start entering particle physics size experiment. Sort of next generation of gravitation, we are thinking here 20 years down the road. And the best way to get a better instrument at some point is make it bigger. That is almost unavoidable. There's only so much you can do in the noise sources. So if you can see here, there's some improved. This is the advanced LIGO sensitivity with the 10 to 20 year upgrade. You probably can get here, but then to go from here to this sensitivity, you need to basically go longer, 10, 20, even 40 kilometers. There are currently 2 long-range projects here. There's an Einstein telescope in Europe, and here in the US, we're seeing something called Cosmic Explorer. Maybe, right now on paper, it's 40 kilometers long. Due to the time and funding of this project, of course, you have to start very early with these things. And here is a little bit the science, what you might be trying to do with it. Here we're looking at the redshift. Here we're looking at the binary in-spiral sources, and then we basically want to see how far we can see it. If you look at something like advanced LIGO, we may reach C is equals 1. And, but with a 40-kilometer instrument, 20 years down the road, we probably see every black hole merger in the entire universe. That is actually quite powerful. I mean, even if you see something before the first stars were born, we may even see some. You could even potentially identify primordial black holes. Of course, now if you see a merger, we don't really know is that something that was always there. We don't really know when it was formed. We can say if it's So I think as we'll just conclude with that, we detected merging binary black holes and neutron stars have been observed for the very first time. That started an entire revolution in scientific evolution, especially in astronomy. Future increase in sensitivity will increase the rate of detectors dramatically. I would say the future looks bright, so stay tuned. Thank you very much.
We have time for a couple of questions.
I was wondering if you could give some more information about the new detectors coming up, and if they're going to be used, for example, for triangulations of positions of mergers, for example, or other things.
The minimum you need is 3 detectors, but you already see that there are zeros in the antenna pattern. So if you have 4 detectors, you can actually do significantly better because you don't have to worry about the zeros anymore. There's of course also the thing, these are very complex instruments, so it's very hard to keep them 100% up. So the best we have sort of achieved is sort of 80% during a run. So you're getting into problems that we have multiple detectors. If you want to have good coverage all the time, you need to actually have 4 or 5 just to be able that you have 3 detectors up all the time. With Virgo together, it was less than 50% of the time. We actually had 3 detectors running at the same time. Of course, we always say that and maybe that's a point I didn't make, that if you have 3 detectors, you can do pointing where it is, and maybe say, maybe I don't care about that. But it's also important because there are 2 polarizations. For us to recover the full waveform, we need 3 detectors. Then when the pointing comes with it, but there is also a distance and inclination ambiguity. So if you want to know the distance, if we know the inclination plane of those systems, and we now want to know where it wants from, we need 3 detectors, and it all comes together at the same time.
Maybe it was just the map projection, but it looks like all of the detectors are kind of along the equator. Are there plans to put them somewhere in South America or closer to the poles?
Certainly Australia would be a good option. It doesn't, at the end of the day, it doesn't make as much a difference. You want to have, of course, the lengths as long as possible. This is not as bad. This is pretty good. And you can do a little better if you put something in Australia, but it's only 20-30% better.
So if you go to the slide with the periodic table, I think there were like 2 elements with like no indication as to how they were formed. So is it that we don't know, or is it that they're only produced artificially or something? I don't know if you can. Yeah, or
4361.
Yeah, is it not known, or what's the situation there?
No, it isn't. I think that's the beryllium. You ask more than I know.
Well, that's a good place to leave it. Let's thank Daniel again.